Okay, now here, spring mass system. So we have a spring here. Okay, this is a closed coil helical spring. Closed coil helical spring with a mass attached to its end. Okay, so this spring, this mass here, when it is being released, it will start to oscillate from point A to B, and then from B to C, and then from C back to B, and then to A, and it will continuously oscillate about its mean equilibrium position, that is at point B. So when the mass is being displaced by an amount of delta, that is when the mass move to the position B, okay, you have a deformation of spring of delta. And spring is an elastic material which obeys Hooke's law. So when it is being released, when the mass is being released, it will tend to extend, the spring will tend to extend by an amount of delta. So when it is extended by an amount of delta, you will have a restoring force or a spring force of K delta, which that the restoring force or the spring force is directly proportional to the value of delta. We know that K, that is the stiffness of spring, which is in Newton per meter, it is a constant. So therefore, the restoring force is only directly proportional to the deflection of spring delta. So you will have a force of K delta that is acting upwards, the restoring force of the spring. So, and at the same time, due to the mass, okay, you have a wave of mg. You have a wave of mg. So therefore, at the equilibrium position, that is point B, you will have two forces. One is K delta and the other one is mg. So at equilibrium position, this K delta should be equals to mg. Okay, the K delta should be equals to mg. So now, when the mass further move vertically downwards by an amount of x, that means the spring extends by an amount of x, so therefore you will have a force, a total force, which is acting upwards, that is K delta plus Kx. Okay, that is K delta plus Kx, and it goes against a downward an upward force of mg. So therefore, when you refer to mg and Kx with K delta, you will have a net force of Kx. You have a net force of Kx, and this net force Kx causes the mass to slide upwards again. Causes the mass to slide upwards. So you have a net force of Kx. Okay, so going against the mg, so Kx plus K delta, Kx plus K delta minus mg, you will have a net force of Kx. Because initially at equilibrium position, we say that K delta is already equals to Kx. Hold on a second. Okay, so we have this. So stiffness of spring is in Newton per meter, and it is denoted by the symbol of K. So you can see when the mass is being released, the spring with the mass will be oscillating about its mean equilibrium position. So K stands for spring stiffness in Newton per meter, and M stands for mass in kg. So assuming a negligible mass of spring and is assumed to be obeying Hooke's law, then the extension or the contraction of the spring is proportional to the applied force within its elastic limit. Okay, within its elastic limit. So the extension and contraction of the spring is proportional to the applied force. So that the K, since the K is a constant, so that is why the extension or contraction is directly proportional to the force that is applied. Okay, so now the spring or the mass will start to move from A to B at mean equilibrium position. So at mean equilibrium position, we say that the total downward forces must be equal to the total upward forces. So therefore, you have mg equals to k delta. M stands for the mass m. Okay, and g stands for the accelerations due to gravity in meter per second square. K is the spring stiffness in Newton per meter. Delta is the extension of the spring. Okay, or sometimes it is being referred as contraction as well. So if the mass is now moved downwards further from B to C through a vertical distance x from B to C from the equilibrium position, the net force in red color, the net force acting on the mass will be shown above, that is equals to kx. Kx, the net force, there will be a net force. Okay, so the next part here, it shows you, okay, delta and x. When the mass has already moved from delta to x, then you have a net force of mg minus the total upward forces, that is kx plus k delta. At equilibrium position, we have already known that mg equals to k delta. So therefore, the net force is only negative kx. Okay, so you have the net force of negative kx. Okay, so the net force acting on the mass is directly proportional to the displacement of the mass from the equilibrium position. The minus sign, that is negative kx, the minus sign only indicates that, okay, the force, the restoring force is acting towards the equilibrium position and in opposite direction to the displacement made by the mass. Okay, the displacement made by the mass. So the restoring force is acting upwards, but the displacement that we measured is downwards, vertically downwards in this case. Okay, so you have the mass, okay, so it will start oscillating. So from point A, then it oscillates to point B. So actually we are referring to the same position here. Point B, then further extends to C. Okay, so when it is at position C, the upward force is greater, so it pulls the mass back to point D and then to E. And at point E, we say, okay, mg is acting, but the restoring force is 0. So the weight of the object or the weight of the mass will pull the spring back to F and then G. And then at G, net force Kx is greater, so it pulls the mass back to H and then to I. And then at the same time, also, okay, at this position, okay, we say spring force or restoring force is 0 at I. That weight is greater, so it pulls the mass back downwards again to J and K. And then it repeats continuously. Okay, if we were to neglect the frictional force due to the surrounding air. Okay, otherwise it will continuously oscillate, we assume. So when the mass is released, it will oscillate in a vertical plane about the equilibrium position. From Newton's second law of motion, we know Newton's second law of motion says that the net force is equals to the product of mass and the acceleration. So you have net force equals to, based on Newton's second law, mass times acceleration. So you have kx equals to ma. Okay, ma is the net force, okay, based on Newton's second law, and kx is the one that we refers to the restoring force of the spring, which is acting upwards. Okay, so when we were to manipulate kx equals to ma, we will have a formula of k over m, which is equals to acceleration over displacement. So kx equals to ma, k is stiffness of spring, x is the displacement of the spring, m is the mass, a is the acceleration of the mass. So if you were to manipulate kx equals to ma, you can get k over m equals to a over x, where x refers to displacement. And earlier in our oscillation part, we got to know that, okay, the omega square, or the circular frequency omega, is actually equals to, omega square is equals to k over m in this case. Earlier we got to know that omega square is equals to acceleration over displacement, if we were to refer back to the previous notes. Okay, so acceleration over displacement at this point, it also equals to k over m. So therefore, we can also equals, or we can also say that omega square is equals to square root of k over m, or which is also equals to square root of acceleration over displacement. The omega is the circular frequency, remember, which is in radians per second. Okay. And we know that omega is actually defined as, for oscillation, as 2 pi over the period time, that is the uppercase letter t, and in this case also equals to square root of k over m. Okay, so we know that t equals to 2 pi over omega, that means the circular frequency, and from there we can say that, okay, and also period or frequency, period is actually equals to the reciprocal of frequency, or 1 over frequency, or you can say frequency is equals to 1 over period time. Okay, so which is equals to 2 pi over omega. 1 over frequency is equals to 2 pi over omega. So if you take 1 over period time, then it will be omega over 2 pi. Okay, so you have this and this. Then it can be rewritten as frequency is equals to 1 over 2 pi to the square root of k over m. Okay, or the period is equals to this. Okay, so you have this, and then we know that, okay, the f actually refers to the Fn, which is called the natural frequency of vibration. And also in the equilibrium position, we have learned earlier that k delta is equals to mg. So you can also replace it with k over m equals to g over delta. So natural frequency, which is earlier equals to Fn equals to 1 over 2 pi square root of k over m, can also be rewritten as square root of g over delta. Okay, so basically here you have 3 formulas that you need to remember. One is based on g as a function of g delta, the other one as a function of k and m, and the other one is based on acceleration and displacement for the period, for the frequency, and for the circular frequency. Okay, thank you for this section. So now, and also if the mass of the spring we denote it as m with a subscript of s. is not negligible. That means if we were to take into account the spring of the mass, earlier we neglect the spring of mass. So if we were to consider spring of mass, mass of spring, then you will have to include, okay, the mass of the spring by taking as 1/3, okay, of ms. Okay, ms stands for mass of spring. Okay, so there is only a little bit of modification here if you were to include the mass of spring. Okay, thank you.